So hi everybody. So it's lecture 7. And we're going to do more number theory today. But roughly, let me just review what we did last time, or at least mention what the main topics are that we'll need to use. So last time we talked about divisibility. So what it means for integer a to divide integer b, and some of the properties that that notion has. Then we talked about the division algorithm, which is just a fancy name for the fact that if you have two integers, a and b, then you can write a as, there's a unique way to write a as dq plus r, where r is this remainder that's very important, that's non-negative in between 0 and d. And then using this notion of a remainder, we developed this idea of congruence modulo m. So we said that two integers a and b are congruent modulo m. So this is a relation between the two integers a and b if they have the same remainder modulo m. So if a mod m equals b mod m. And the key property of this congruence that we proved at the end of the last lecture was this property of arithmetic modulo m, which was that if you take two integers a and b and you add them, then the sum is congruent to the sum of the remainders. Modulo m. And similarly, if you take two numbers a and b, then the product, two integers, is congruent to the product of the remainders. Now, this is just a rephrasal of the properties that we proved at the end of the last lecture. Some people might find this easier to understand. And in English, what this is saying is that, the remainder modulo m of the sum of two numbers, the remainder of the sum is the sum of the remainders. And similarly for the product, that's what this is saying conceptually. So that's a quick review of what we did last time. And we also talked about binary representation of integers. We showed how the division algorithm can be used to find binary representation. In particular, we saw that 45 is equal to 101101 in base 2. And we had one unfinished task, which was in the beginning of or earlier in the lecture, we had this challenge, which is, I asked you, what day is it going to be in 5 to the 45 days from now? And now it was Tuesday. And this translated to this question of what is 2 plus 5 to the 45 modulo 7. And I never answered this question. I developed all these tools, notions of congruence and so on, and now I'm going to show you how to use them to solve this problem. So before I do that, any questions on this recap?
So like a plus mod m just equals to a mod m plus b mod m. So that is like how we interpret it.
It's not equals to, it's congruent.
Yeah,
A mod
congruent,
m
sorry.
plus b mod m modulo m, yeah. So what this is saying is you can take the remainder before doing the arithmetic, and you get the same answer as if you took the remainder after doing the arithmetic. So let's use these properties to solve this problem. So this is an idea which is called repeated squaring, and it's formalized in algorithm 5 in the book, in section 4.2, I believe. So what's the idea? So remember, we express, the key is, so step 1 is to express the exponent as a sum of powers of 2. So express, in this case, I'm going to run it on this. I'm just going to show you the algorithm on this example. So express 45, the exponent, as a sum of powers of 2. And we have the binary expansion, so we have that, right? It's 1 plus 2 squared plus 2 cubed plus 2 to the 5. That's what the binary expansion tells us, right? Okay, so we did that last time. We showed how to find that binary expansion. Okay, so now step 2 is where the modular arithmetic comes in and where we use some interesting properties. I'm going to express 5 to the 45, which is this thing I'm interested in, as 5 to this binary expansion. Modulo m. This is just because this is equal. And now by just basic rules of exponentiation, I see that this is congruent to 5 to the 1 times 5 to the 2 squared times 5 to the 2 cubed times 5 to the 2 to the 5 mod m. Okay, so I'm expressing this as a product of powers of 5. In each case, the exponent of 5 is a power of 2. Now, why is this a useful thing? So step 3 is compute all of these, all of these powers of 2. So let's just write it this way: compute 5 to the 1, 5 to the 2 squared, 5 to the 2 cubed, 5 to the 2 to the 5 modulo m by repeated squaring. So what do I mean by that? Well, okay, so 5 is congruent to just 5 mod 7. Okay. 5 to the 5 squared is congruent to, okay, 25, which is congruent to, so what's the remainder modulo 7? Well, 21 is the largest multiple of 7, so you get 4 mod 7. Okay, but now I get to the first interesting one, 5 2 squared. Now I could try to compute what this is. It's a big number. Or I could use this observation that this is just the square of the previous thing, right? This is just 5 squared squared. And now what would I do if I wanted to save myself some effort?
4 square.
Yeah,
Plug
just
in
plug-
your value. Yeah.
Yeah, plug in the value from the previous step. So this is congruent to 4 squared, which is congruent to 16, which is congruent to 2 modulo 7. And now you have 5 to the 2 to the 3. What do you do there?
Four cubed.
4 cubed. Where did you? 4 squared. Okay, let's be more systematic. So the key pattern here is that 5 to the 2 to the 3 is 5 to the 2 to the 2 squared. Okay, so the key pattern here is that 5 to the 2 to the k plus 1 is 5 to the 2 to the k squared. This is just a sort of high school algebra fact, though you may not have seen it in this form before. But now this is good, right? Because I just computed 5 to the 2 to the 2. So this is now this congruent to, 2 squared. It's congruent to 4 mod 7. And then 5 to the 2 to the 4 is now just, again, congruent to the previous one squared. Hence the name repeated square. Then 5 to the 2 to the 5 is congruent to 5 to the 2 to the 4 squared, which is congruent to 2 squared, which is congruent to 4. Okay, so this is the key property here. Now this is this is, looks, you know, so the thing I've used here is the property of modular arithmetic, right? That I can, you know, I can reduce modulo 7 before doing the arithmetic. And now, you know, the punchline here is I computed the remainder of this giant number, modulo 7, without ever computing it. Right? 5 to the 2 to the 5 is huge. Like, it's a really, there's no way, you know, you don't really want to be doing division with numbers that are that big. But nonetheless, I have all these remainders. So now step 4 is just plug all these back in. Step 2. So now you get 5 to the 45. So remember, it was a product of 5 to the powers of 2 written here. So this is just going to be the product of, like, I computed these, right? This is 5 to the 1. This is 5 to the 2 squared. This is 5 to the 2 cubed. And this is 5 to the 2 to the 5. So this is congruent to 1 times 2 times 4. Sorry, not 1, 5 times 2 times 4 times 4, which is congruent to, I don't know, 10 times 16, which is congruent to 3 times 2, which is congruent to 6. And so the conclusion is that 2 plus this number is congruent to 8, which is congruent to 1 mod 7. So it's, I believe the way we numbered it, it's Monday. 5 to the 45 days in the future. Okay, so this is, you know, you can formally describe this. It's done in the book, but the reason I'm including in this lecture, there are 2 reasons. One is it's a good practice with modular arithmetic, but there's actually a more practical reason. So the remark, which I'll make later, is that this is a key operation in cryptography. So, you know, all internet security, all that stuff is based on number theory. We'll discuss this in a couple of lectures. And one of the key operations is to be able to raise things to a huge power modulo a prime number. So any questions about this repeated squaring algorithm?
Yeah, so is it just a coincidence that it happens to be 2, 4, 2, 4, like oscillating, or
that is a great
some
question.
pattern?
So that's a great question. Is it a coincidence that it's 2, 4, 2, 4? So hold on to that question, and let's think about that after the next lecture. We'll have some more tools to understand. That's a great question. Is it a coincidence that it's 2, 4, 2, 4? So actually, I mean, okay, there's kind of one thing we can kind of easily note is that once you get into this 2, 4, 2, 4 pattern, right, it's going to keep on going on forever, right? Because you're going to get 4, then you're going to square it, you're going to get 16, which is 2, then you're going to square it, you're going to get 4. So you can actually prove that this will continue forever. So it's not a coincidence, but we'll try to understand why this is happening later. Maybe. Any other questions? Okay, so for today's lecture, there are 3 topics. One is prime numbers. The second is what is the second topic? Second topic is, yeah, greatest common denominator, greatest common divisor. And the third topic is the Euclidean algorithm, which is a very important algorithm in number theory, which we'll learn about, and Bézout's theorem. So let me start by talking about prime numbers. So here's a definition. Maybe many of you have seen it before. So an integer p strictly greater than 1 is prime if it has no divisors other than 1 and itself. Okay, so for every number, 1 divides that number and the number divides itself. The number is prime if there's no other divisors. So formally, we might add, so formally, P is prime if and only if, so a number P bigger than 1 is prime, if and only if, for every K, that's a positive integer, if K divides P, then K equals 1 or K equals P. That's in propositional logic what the definition is saying. There are no divisors other than 1 or P. And okay, not all numbers are prime. Okay, so 3 is a prime, 4 is not a prime. The numbers that are not prime are composites. So an integer C strictly bigger than 1 is composite if it is not prime. And not prime means that it has some divisor other than 1 in itself. So what that means is, that means C is equal to A times B for some integers A and B that are not equal to 1. Okay, so you can divide C by something other than C in itself. So any questions about the definition?
So what would 1 be if it's not prime and it's not composite? Or is it prime? It's definitely not composite.
That's a good point. 1 is neither. 1 is not defined to be prime or composite. 1 is just 1.
Okay.
Okay, so the reason primes are very important, but the reason they're really important is that they're the building blocks of all other numbers. And this is captured by a very important theorem called the fundamental theorem of arithmetic, which I'll write down now. So theorem and the theorem says every number can be uniquely written as a product of prime numbers. Okay, so every integer n strictly bigger than 1 can be written uniquely as a product of primes. Let's call them P1, P2, P3, Pk, listed in non-decreasing order. Okay, so what does that mean logically? So formally, this is saying that for every n bigger than 1, there exist unique P1 through Pk such that they're all prime. P1 through Pk are prime. P1 through Pk are non-decreasing. So that means it just means you sort them P1 less than P2, less than or equal to P3, less than or equal to Pk. And n is a product of these numbers. Okay, so what this is saying is, okay, some primes may be repeated. They may appear a bunch of times. The reason we insist on this non-decreasing order is just to get it to be unique, right? If we don't say the order, if we don't talk about the order, then you can just take the same numbers and shuffle them around and say, hey, that's a different factorization. We just want to say that once you sort them this way, there's only one way. That's why we talk about non-decreasing order. So for example, this theorem implies that, okay, like 15 is equal to 3 times 5. 24 is equal to 2 times 2 times 3, etc. So I'm just listing them in non-decreasing order. I'm saying there's always a way to do this, and there's only one way. So so the goal of this lecture is going to be to prove this theorem. And this theorem has two parts. It has existence of a prime factorization and uniqueness. There are two parts, and we're going to do both of them. But before we do that, any question about the statement of the theorem? Yep.
I think it might be just a simple mistake, but I think there should be an extra 2 in 24.
Oh, sorry. Yeah, of course. Yeah, okay. 2 times 2 times 3 is not 24. 2 times 2 times 2 times 3. Thank you. Okay, so let's prove this. So first we're going to prove existence, which is easier actually. And the key in proving existence is the following proposition, which I'm going to call lemma 1. So lemma is maybe a new word here for us. A lemma is just a proposition that's going to be used to prove another proposition. Okay, it's nothing different. It's just used to emphasize that we're going to use this to prove this is being proved in service of some other more important proposition. And maybe that it may be useful in many different proofs. So it's like, it's like a piece of argument that's going to be used in other proofs. So here's lemma 1. Lemma is if you have a composite number, if c bigger than 1 is composite. I mean, okay, better be bigger than 1. There is a prime p such that the prime divides c. So if a number is composite, there's a prime that divides. Now, what's the content of this lemma? So a composite is something that's divisible by a number that's not 1, right? So we know a composite is already divisible by something. What this lemma is telling us that actually a composite is always divisible by a prime. So any intuition about why this is true before we get to the proof? Before I explain the proof to you? Why do you think this is true? If so, how would you go about proving it?
I think that you could, if C is divisible by a number that isn't prime, then it would be divisible by a composite number. You basically apply the algorithm again, and then you keep on doing this as you get smaller and smaller until you probably get down to like the case of 2, and then you say that 2 is prime, and then it works your way back up, or 3 or some number.
Okay, yeah, you're on the right track. You're saying, well, just keep dividing C by numbers until you get to one that's prime. And I guess what you have to show is that at some point you will get to one that's prime. So that's the part that's a little tricky to formalize, but you're on the right track. So let me tell you the proof, which kind of does go this way. Okay. Okay, I'm temporarily going to switch to this. Okay, so okay, so let's so suppose C is composite. So assume C greater than 1 is composite. Okay. So the key now is I'm going to look at the set of all divisors of C. So let S be the set of all positive integers D such that D divides C. Okay, and D is strictly bigger than 1. We don't want 1 is kind of a boring divisor here. We don't want that. Okay. So now I'm kind of going to do what you said. So first I'm going to notice that set is not empty. So notice S is not empty since what? What number is in there?
C itself.
C itself, yeah. C is in S. Okay, so also notice that S is a subset of the integers 1 through C, because no number bigger than C is going to divide C, right? In fact, 1 is not even in there. It's a subset of the integers 2 through C. So now I'm going to do something which is done a lot in proofs. I'm going to choose the smallest element of this set. So let Q be the smallest. So that means the least as an integer element of S. So now we'll show that this has to be prime. So that means we have to show that nothing else besides 1 and Q divides Q. Any thoughts on, I mean, this is where we're going to invoke the idea that was mentioned earlier. Let's assume for contradiction that it's not, right? So if not, then we can choose some number A that's not equal to 1 and not equal to Q, such that A divides Q, right? That's what it means to be composite, right? If it's not prime, it's composite. You can choose some A that divides Q. And now what's the problem?
We have a number smaller than Q, which all divides the original number C. So we've created a contradiction.
Exactly. So, but since Q divides C, we have A divides C, but A is strictly smaller than Q, which is a contradiction. So we have proven that we've proven the lemma by choosing this trick of choosing the smallest element is very useful. It comes up a lot in a lot of different proofs. Okay. So using this, I can now prove the existence part of the fundamental theorem of algebra. But any questions about this before I proceed?
Can I see the lemma again real quick?
Sure.
Wouldn't this have to also include the fact that P is not equal to P?
Yeah. So I said that, right? So A is not equal to P.
Okay.
Right? Because I used that Q. I mean, so I mean, I used that A is not equal to Q. Maybe that's what you meant, right? A is not equal to Q, so A is strictly less than Q. Yeah, we did need that. Okay, so let's take like a 30-second break since this is around the time that things start happening with my screen sharing.
So the D that you wrote in like the provement part, D is a random number, is a element of the integer. Is that?
Yeah, it's not random, right? I use this set builder notation. S is the set of all positive integers such that D is bigger than 1 and D, it's a set of all divisors of C that are not equal to 1. Yeah. Okay, so let's now prove the existence part of the fundamental theorem of arithmetic. Okay. Okay, so the claim is for any positive integer, you can write it as a product of primes. So here's the proof. So suppose n is bigger than 1. So the idea of the proof is pretty simple. So if n is prime, I'm done, right? If n is prime, n equals n is a prime factorization. So that case is easy. Now, if n is not prime, what should I do?
You can find a prime vector of it.
Yeah, by lemma 1, right? So if n is not prime, if n is composite, lemma 1 implies well, implies n equals n1 p1, or let's write it as p1 n1. For some prime p1 that's strictly less than n, and of course this n1 has to also be strictly less than. Okay. So now we're going to repeat this process with n1. We're going to, if n1 is prime, then we're done, right? If n1 is not prime, then we apply lemma 1 again, and we get a factorization of n1, right? So if n1 is prime, we are done. Otherwise, let n1 be equal to p1 times n2 for some p2 less than n1 and n2 now strictly less than n1. And now we're just going to keep repeating this process, right?
Shouldn't it be n1 equals p2 n2?
Oh, sorry. Yeah, p2. My bad. Yeah. Okay, so repeating this process, Kate, let's say k. Okay, so we keep repeating this process until we reach a prime, right? Or so actually, let's put it this way. Let's say if we repeat this process k times, we obtain a factorization n equals p1 n1, which is now p1 p2 and 2, which if you do this k times, you get p1 p2 all the way up to let's see. So if you do it once, you get P1 N1. So if you do it K times, you get P1 through Pk and K. But the key point is this process can't go on forever, right? So why can't this process go on forever?
Because each n is finitely big.
Yeah, because the numbers are strictly decreasing, right? So since nk is strictly less than nk minus 1 is strictly less than nk minus 2 all the way up to n1, this process must terminate in, let's say, t steps for some capital T is strictly less than it. And by terminate, that means that it actually finds a prime number, right? Because it either finds a prime or decreases n, right? And so you can't decrease infinitely many times. So at some point, you have to find a prime. So for that particular T, we have n equals n1, n2, all the way up to n, I guess, T. Oh, sorry, P1, P2. Or I guess we just write it as Pt, nt, and nt is prime as desired. Okay, so it's not a complicated thing. It's just a fancy way of saying, oh, you can pull out one prime factor every time. That decreases the number. If you do that enough times, you'll get a prime factor. That's a proof of existence. Any questions about the proof?
What's after terminate?
Terminate in t steps.
Aren't we supposed to prove that like any integer bigger than 1 that can be factorized to like increasing order prime number product?
Well, so, okay. Once you get this, you can sort them in, you're right. You can, and if you want, you can then sort these factors in non-decreasing order. And then that's a non-decreasing factorization. You're right. So finally, you can sort the primes in non-decreasing order. So there's one more step at the end. So yeah, that's not hard to guarantee. You just rearrange them.
Would this also be a uniqueness proof because each set S only has one smallest element?
This is not a uniqueness proof because in each step of this procedure, we didn't say which prime you choose, right? What if in step 1 you have 2 different choices? Right? Like a picture of the proof is something like you start with n, either it's prime, in which case you're done, or you get n1 p1, and then n1 is either prime, in which case you're done, or you get n2 p2, and then this is either prime.
We can't
or
see
you're
your
done.
screen. Can't see what you're writing.
You can't see what I'm writing? Okay. Sorry. So what I was saying about the proof is that here's a picture of what's going on in the proof. is that you start off with this number n, and you factor it as n1 p1. So either this number is prime, in which case you're done, or you factor it, then either this is prime, or you factor it as n2 p2, then either this is prime, or you factor it as n3 p3, etc., etc., etc. And this, we never said this process is unique, right? Because the first factorization may not have been unique. So we did not prove uniqueness, we just proved existence. Does that answer the question?
Yeah, it does. Thank you.
Yeah. Okay. Okay. So there is one more cool thing we can prove with this lemma, which I might as well show you since it's so beautiful. So this is a theorem due to Euclid, which simply says there are infinitely many prime numbers. Okay. So let's see how this follows from the lemma. So it's a proof by contradiction. I'm going to assume for contradiction there are finitely many primes. So P1 through Pn, and that's where I've used the finiteness, right? That I can list, the fact that I can list them as P1 through Pn, that's equivalent to saying that there are finitely many. Otherwise, I wouldn't be able to, right? So this is this sort of hypothetical list of all prime numbers. If there were finitely many, I could make such a list. So what I'm going to do is I'm going to produce a prime that I'm going to produce a number that's not on this list and is prime. The idea is to consider the number q equal to the product of all these numbers, p1, p2, p3, pn plus 1. So first of all, I claim that q is not prime. Why is q not prime?
Because it's not in the list of p's.
Why is it not in the list of p's?
Since it's a product of all the.
Yeah, it's bigger than everything in the list, really, right? So
it's even.
So notice, no, we don't know if it's even. Notice that q is not prime, since q is simply bigger than everything on this list. Right? That was the list of all primes. So it's a funny thought experiment. We're imagining for a moment that there are only finitely many primes, right? Namely that there's this list of all primes. Right? This is a list of all primes. So if it's not on the list, it's not prime. Okay, that means it has to be composite. And now what do we know about composites by lemma 1? Well, they have to be divisible by prime. So by lemma 1, there is a prime, somebody on this list, right? So by lemma 1, there is some pj on this list such that pj divides q. So this is it's a bit of a tricky proof because you're assuming that there are only finitely many primes in order to make this happen. But yeah, one of the consequences of that is lemma 1 implies if there are only finitely many primes, then one of them has to divide q. Okay, now this is a little fishy. So Pj divides Q. Now what else does Pj divide?
Also like Q minus 1.
Yeah. So notice that P divides the product of P1, P2 up to Pn. In other words, P divides Q minus 1. So P divides Q and P divides Q minus 1. That's kind of fishy, right? What can I conclude from that? Sorry, Pj divides the same Pj.
You conclude that no such PJ exists because no number divides a number and the number directly after it.
Yeah, and the way we see that formally is, therefore, P divides Q minus Q minus 1, right? Because if P divides A and P divides B, then P divides A minus P. Or P divides 1, which is absurd. Which is a contradiction. Or Pj, sorry. So therefore, our assumption is wrong, and there are infinitely many primes. That's the proof. That if there were finitely many, you would have this method of constructing a number not on the list, and then that would neither be prime nor composite, which doesn't make sense. It's a very slick proof. It's one of the real gems of ancient mathematics. I mean, mathematics generally. Any comments or questions on this proof? Okay, so let's move on to the second topic, which is greatest common denominator. So this is all going to be in service of proving the uniqueness part of the fundamental theorem of algebra. Here's the key definition. If A and B are integers, they could be negative, not both 0. So at least one of them should not be 0. Then, sorry. Then the greatest common denominator of A and B is the largest positive integer such that D divides A and D divides D. I mean, it's what you expect, right? Then the greatest common denominator of A and B, common divisor, sorry, I keep saying denominator. Right, it's the largest common divisor. So for example, what's the greatest common divisor of 10 and 36? Well, according to the definition, it's the largest number that divides both of them. So how would you find that? Well, you would just write down all the numbers that divide each of them. So you have divisors of 10. Sorry, I think someone is. So you have the divisors of 10, which is a set 1, 2, 5, 10. Then you have the set of divisors of 36, which is the set 1, 2, 3, 4, 6, 9, 12. Sorry, what's after that? 18. Right? And now you say, okay, what's the largest number that's in both of these sets? Well, that's this. So this equals 2. So any question about the definition of greatest common divisor? Okay. So what I'm going to show you now is, yes.
So because these are basically the factors of the numbers, it's also called GCF.
It's also called what? GCF. Yeah, it's the same thing concept as GCF, greatest common factor. Yeah. Okay, so what I'm going to show you now is, so this is one way to find the greatest common denominator. List all the list the greatest common divisor. List all the divisors and find the largest one. But now I'm going to show you a much faster way. And that is called the Euclidean algorithm. And that is a much faster way.
Is that like the similar thing as we used yesterday, like to change number to binary? Is that kind of similar pattern? Like
Yeah,
do it again.
Yeah, it is a similar pattern. It's not the same thing though, but yeah, it's not actually, it's different. There are some similarities. You'll see what it is. Okay, so the key observation is the following, is that if you have two integers, a greater than b and b is greater than 1, okay, then no, if you have two integers, a is the bigger one, and you divide a by b using the division algorithm, and a is equal to bq plus r for r between 0 and b, r is strictly smaller than b. So you just divide a by b, right? You get some remainder. Then the GCD of a and b is equal to the GCD of b and r. Okay, this is not obvious. This is not an obvious fact. We're going to prove it in a moment. So let's, this fact is actually going to follow from an even stronger lemma, which I'm going to prove in a moment. It's going to follow from lemma 2. Which is that if you have a bigger than b, bigger than 1.
Professor, can you go back to previous page for just like 5 seconds?
Yeah. Okay.
Okay.
So, or actually, I'll just write it here, right? So, it's under the same assumption. So, if a is equal to bq plus r, with r remainder like this, then for every positive integer d divides a and d divides b if and only if d divides b and d divides r. So what this is saying in words is that the set of common divisors of a and b is the same as the set of common divisors of b and r. It's not saying that the set of all divisors of a and b is the same as the set of all divisors of b and r. It's just saying that the set of common divisors doesn't change when you do this division. And that obviously implies that the greatest common divisor of a and b is the same as the greatest common divisor of b and r, because it's just the largest element of that set of common divisors. So let's prove this. So it's an if and only if. Let's prove one direction. So assume d divides a and d divides b. I'm going to use this fact about divisibility that we proved in the last lecture. So it follows that d divides A minus BQ, right? Because D divides A, D divides B, that implies D divides BQ, that implies D divides A minus BQ. But what's A minus BQ? That's just R, right? So D divides R, and consequently D divides B. We're just rewrite, we already knew that, and D divides R. Okay, so it's not hard to see this. Other direction is skipped. It's easy. You can do it later if you want. But this is the key lemma, that the pair AB has the same set of common divisors as the pair BR.
How did you get that it follows that D divides A minus BQ?
Yeah, let me just fill this in here. So here the steps were D divides A, D divides B, D divides BQ, because right, if you multiply B by some other integer, it still divides it. And then D divides A minus BQ.
Okay, thank you.
Yep. Okay, so we've proven this little observation. So this follows from lemma 2. Lemma 2 is what's written over here. And now with this in hand, we have a very efficient and interesting way of computing a GCD. So I'll show it to you on an example. This is the Euclidean algorithm. It's formally described in the book as, I think, algorithm 1. So example. So the example is, let's say I want to compute the GCD of these two somewhat larger numbers. GCD of 252 and 198. Okay. Well, what the key observation is telling me, so in this case, this is my A and this is my B, right? Is that if I divide A by B and get the remainder, then this is equal to the GCD of B and the remainder. So let's do the division. So 252 is equal to 1 times 198 plus 54, right? So now the key observation is telling me that this GCD is equal to the GCD of 198 and 54. Now, why is this better than what I had before?
Because it's smaller numbers.
Yeah, smaller numbers. So let's do it again, right? Let's divide 198 by 54. So I believe that's 3 times 54. And you get 36 as the remainder. Right, 3 times 54 is 162 plus 36. Yeah. And again, by the key observation, you get that this is the GCD of 54 and 36. So I'm making the numbers smaller and smaller without changing the GCD. Okay, now I just keep doing it, right? 54 is equal to 1 times 36 plus 18. And now I'm actually in luck because 36 is just equal to 2 times 18 plus 0. So now you stop. Because 18 divides both of them. So I just found the GCD of these two kind of big numbers without listing the common divisors. Okay, so the algorithm here is repeatedly express A as BQ plus R, and you use that the GCD of AB is equal to the GCD of BR. And then stop when you get a remainder of 0. This is an informal description. A formal description is given as algorithm 1 in the book. But the idea is very simple. You just repeatedly divide the larger number by the smaller number. Okay. So any questions about what this algorithm is? Okay, so now I want to highlight one feature of this algorithm, which may seem kind of like weird that I'm emphasizing this, but it's actually the key to proving the fundamental theorem of algebra and to many other things we're going to do. So here's an observation. So eventually the GCD we output was this, right? 18. And we arrived at it by chaining together a bunch of these equations that we got from the division algorithm, right? But now what happens if we try to use those equations backwards to express the GCD in terms of the original input numbers, namely 252 and 198. So I'm going to do a weird computation here. I'm going to say 18 equals 54 minus 1 times 36. Okay, but now I know how to express 36 in terms of 54 and 198, right? So this is equal to 54 minus 1 times 54 minus 18. Or no, sorry. What am I doing? Right. I want to substitute. What am I saying? I want to substitute the second equation into the third equation. This is now 198 minus 3 times 54. Okay, so I got rid of the 36 now. I only have the 198 and the 54. And now, again, if I group the 54 terms, so this is I have minus 1 times 198, I guess plus 4 times 54. And now I'm going to use that. I know what, I can express 54 in terms of 252 and 198, right? So this 54, I'm going to substitute in that equation. So this is minus 1 times 198 plus 4 times 252 minus 1 times 198, which is, when the dust settles, this is minus 5 times 198 plus 4 times 252. Okay, so why did I do all this arithmetic? So the key point is I expressed the GCD. This is the GCD of the two numbers, 252 and 198. Sorry, I should write it more clearly just to make sure what's equal to what. I express that as some integer times 198 plus some integer times 252. So the key observation here is, if I look at the division steps in reverse, so I just say using the division equations, in reverse, I mean, this is not a formal statement, we can express the GCD of two numbers as SA plus TB for some integers S and T, which may be negative. Okay, so this is the sort of key additional feature of this algorithm I want to emphasize. So one is that the algorithm allows you to compute the GCD because it keeps replacing numbers by smaller numbers until eventually it has to stop. And the second is it allows you to express the GCD as a linear combination, is the word we use here, of the input numbers. Okay, so there are 2 points. The first point is that the algorithm terminates. That's just because the numbers get smaller. The second one is it gives you this expression of the GCD as a linear combination. So any questions about this example or these two claims that I'm making?
What's the purpose to finding this as a linear combination?
Yeah, so that's a great question. It's a bit odd. So I'm going to use it in the next step. It's going to be a key step in the proof of the fundamental theorem of algebra. So this linear combination fact, so okay, we skipped a formal proof of this, right? So unlike a lot of what we're doing in this course, we didn't formally prove these two claims. So we have these two claims. So claim one is that the algorithm always terminates. And the reason is just the numbers get smaller. Actually, that you can easily write a proof. And then claim 2 is actually so important that it has a name. It's called Bézout's theorem. So I'm going to write it. So claim 2 is, I'll write it on the next page. It's called Bézout's theorem. And it says if A, B are integers, not both 0, then there are integers S and T in Z such that the GCD of A and B is equal to AS plus BT. So the proof, we'll skip the formal proof for now, but follows from Euclidean algorithm, follows from the Euclidean algorithm. Because you can always do that back substitution. That's, I mean, you can write a formal proof. The reason we're skipping the proof is we haven't studied induction yet. We'll do that later. Skip formal proof for now. You will prove this later in chapter 5. But I showed you why it's true. That's called Bézout's theorem. Now, great question. Why would we care about this, right? Why is this important? The reason this is important is that this allows you to prove a very important lemma called Euclid's lemma, which sounds intuitively clear, but actually I don't know any way to prove it other than by doing this. Okay, so here's what Euclid's lemma says. It says if A divides BC and the GCD of A and B is 1, so they have no common factors, then A has to divide C. Okay, so if you divide a product of two numbers and you don't have any common factors with one of them, you have to divide the other one. That's what this says. So before I prove this, any questions about this statement?
Yeah, could you repeat what it means?
Euclid's lemma?
Yeah. If you divide
Well,
a-
it's saying if A divides BC, so if A divides the product of two integers, and A does not have a common divisor with the first integer, namely B, then it has to divide the second integer. That's what it says.
got it. Thank you.
So by the way, I mean, this situation comes up a lot, so I'll just write a definition. Two integers, A and B, are relatively prime if their GCD is 1. That just means they don't have any common divisors. It's a good terminology, right? Relatively prime. There's nothing that divides both of them. So let's prove this lemma. This is where Bezout's theorem is going to be crucial. There's a tricky, sneaky proof. Like, I actually don't know how people originally came up with this. It's the first, I would say, really clever thing in this course, to use Bezout's theorem to prove Euclid's lemma. Okay, so we're given this. So assume A divides BC and A and B are relatively prime. Well, let's use Bezout's theorem, right? So by Bezout's theorem, we can choose some integers s and t such that as plus bt is equal to 1, right? Sorry, this doesn't look, the handwriting is not very good, so let me fix it. Okay. Just a sec, let me plug in my charger. My battery is getting a little low. But maybe while I'm doing that, just try to think of what the next step might be. Okay. So as plus bt is 1. Now my goal is to show that A divides C. So I'm going to do this really sneaky thing. I'm going to say observe that C is equal to C times 1, which is equal to C times AS plus BT, which is equal to CAS plus CBT. Okay. So now I claim this is really good.
Professor, I think your screen is frozen.
My screen is frozen. Okay. Can you see it now? I'm not writing anything. I'm not writing anything. Can you see the screen?
Yeah, it's fine.
Yeah. Okay. So what's good about this is I wanted to show that A divides C, but now I've written C as a sum of two things. The first one is CAS. Does A divide CAS?
Yeah.
Yeah, because A is in there, right? And does A divide CBT?
Yeah, because
Yes.
divides BC.
Yeah, because A divides BC, right? So observe, sorry, that A divides CAS and A divides BCT. So A divides the sum.
Other question?
until A divides C as desired.
In
Yes.
In the statement of the proof where you said assume A divides BC, should it say and GCD of AB equals 1? Or just,
Yeah, it says GCD of A and B equals 1.
okay, I meant like right under that line, you know.
Oh, yeah. Sorry, I forgot to write. Yeah, equals 1. Correct. Yeah. Thank you. Okay, so this linear combination AS plus BT allowed us to show very easily that A has to divide C. Okay, so the structure of the proof is, I mean, where did this come from, right? The structure of the proof is we defined the Euclidean algorithm. We used it to, well, show, or at least to informally show that Bézout's theorem is true, that the GCD is always a linear combination of the two numbers. And then we use that fact to prove Euclid's lemma. Okay, so what's the corollary of Euclid's lemma? Corollary is just a proposition that follows from previous propositions. Corollary is if P is prime, and P divides a product of a bunch of numbers, then P has to divide one of them. Right. So the reason is, well, P is prime. So one thing I should say about, prime is relatively prime to every number other than itself. Okay. So in this case, P is relatively prime to A1, A2, A3, A4, etc., etc. And okay, I'll leave you to read the proof of this in the book. It follows from Euclid's lemma. Since P is relatively prime to each of those numbers. Oh, sorry. Well, okay. Okay, yeah. Okay, that's not quite right. Since for each AJ, either P divides AJ or P is relatively prime to AJ. So, what I've written here is just a fact, right? If you have a prime, if you have a prime and some other number, well, either it has a common factor, in which case a common factor is itself, a common non-trivial factor, in which case P divides AJ, or it doesn't, in which case they're relatively prime. And the corollary, so this is exactly the setting of Euclid's lemma. And by applying Euclid's lemma repeatedly, you can prove this corollary. Okay, so we've run out of time, but next time I will finish the uniqueness part. But you can see where this is going. This seems kind of useful for something like the fundamental theorem of algebra. Okay, so yeah, that's it for today.
Thank you.
Thank you.
Thank you.
Thank you.
Professor Nikhil.
Yes.
So I'm Jason. So I made up the first two quiz, and I'm gonna